For our second example, we're going to now analyze and answer questions about inflection points. So let's talk about an inflection point on the graph of f and how it relates to concavity. So if you see in the example, right, I have this yellow dot. This is the graph of f in black. X versus y, input, output, okay? If this shape were to continue, I think we would see that on the far left, I have concave up. Then at this relative max, I have concave down. Then I have concave up, followed by concave down, and then lastly another concave up period. All right. What they mean by an inflection point is where is the exact location that the graph of f changes from one concavity to another. So if I'm looking here, this is concave up. Somewhere on this increasing part of the graph of f, it's going to switch to concave down. So somewhere over here, I have an inflection point where I'm circling. Somewhere over here, where I'm circling, I have another inflection point where I'm going from concave down to concave up. So I see an inflection here. There would be one here, here, and over here. Now, to find the exact location of those, okay, it's not about that the slope is changing at the inflection point. Clearly we can see, for instance, let's look at this secondary one in the middle here. If right here where I'm putting my cursor is the inflection point, between the maximum and the minimum, somewhere it's going to switch from concave down to concave up. Okay, we have a general location of it. Notice the slope is still negative. Negative slope, negative slope, negative slope. Okay, but if we actually take, as the directions say, and trace and come along here, okay, what we can see are the slopes. We can see the slopes of the tangent lines. Okay? What we are looking for is when the slope changes from increasing to decreasing. So notice something. 5.4, 5.6, 5.7, that's increasing. 5.9, then it goes to 6. But then it switches to 5.9, 5.8, 5.7. Those are decreasing slopes. So while they're still positive, there is a trend that's happening. Right when x is negative 6, when x is negative 7 rather, that is the switchover point from increasing to decreasing. So as you can see graphically, that would be exactly where the smile turns into a frown. Okay? Take that same point, we can come over here and say, okay, look, 1.23, 26, these numbers are getting smaller, but then they're going to switch over at negative 2, and now they're changing again. So at negative 2, I have this concave down switching to concave up, and the trend on either side changes as well. Okay, so far I have negative 7, I have negative 2. I think you can start to anticipate they're going to give you some nice numbers for this. So right around 2, I have a switch from happy face to sad face. 2 is another answer. And then as I continue right here around 4, I also have a switch. So when I go to type in my solutions, I have 4 locations where I have the switch from sad face to happy face. I have them at negative 7, negative 2, 2, and 4. And that would be correct. All right, so key information is that inflection points are found graphically where the slopes or the derivative changes from an increasing to decreasing or from decreasing to increasing. What I decided to do was to take 5 examples and go through them, submitting my answers, but then also showing you the Delta Math answers. So it's kind of like I'm the teacher through Delta Math, but at least you get my explanation of how to do the problems. So in our introduction, we talked about concavity. We talked about the fact that we can have concave up, which looks like a smiley face, or concave down, which looks like a frown face. Let's take a look at these examples and see if we can build on this explanation by answering the questions. Given the graph of f, so right now as I'm looking at that, I'm thinking, okay, x is x, y is y. All right, we are determining the intervals on f of x where it is concave down. So I'm looking for sad faces, basically. So on the left here, this is a smiley face, uphill. Then somewhere over here, it's going to switch over to downhill, and then back up to uphill again. Okay? So uphill meaning like happy face. Happy face, sad face, happy face. So concave down is going to be over here somewhere related to this sad face. Now, they're going to help us mathematically by dragging the yellow point in order to graph on the same picture the graph of f prime. So this is a really cool feature of this program. So as you can see, I can grab the yellow dot and I'm bringing it down, and I'm going to stop right here for a second. Negative slope, negative slope, negative slope, negative slope, and then it reaches a bottom point where the slope is 0. So notice why it crosses the x-axis now. M slope is 0. And then it switches back to, excuse me, positive slopes. All right, so here I am, positive slope. So right here, when x equals -1, I have a positive slope. And then I can keep going up, positive, positive slope, positive slope. Then again, it reaches that top where the slope is 0. So notice now I have an x-intercept of 0. Back to negative slope, and then it switches back to positive slope. Okay, so what's in black is the graph of f. What's in orange is the graph of f prime. Now, when we talk about concavity, the best place to see concavity is going to be where f prime is decreasing. F prime is decreasing. So if you notice, right here between 0 and 4, that is the only place on the orange graph where I have decreasing. It goes from high to low values. Okay. Also notice on f of x that I have, it's also part of the frown face. Right here I'm highlighting. So where this ends is at 4. At 4 it switches back and goes to an increasing part of f prime. So what you need to write down if you're taking notes is that to find concave down from the graph of f prime, you are looking for decreasing parts of the graph. When you have increasing parts of the graph of f prime, that will indicate intervals on a concave up part of the graph. So I can come right down here and I can say between 0 and 4, 0 to 4 are decreasing parts of the graph and submit my answer. And here's the answer we get. Well, this one really is going to test your knowledge of notation, right? So twice differentiable function just means you can take it the first derivative and the second derivative. It's on the interval between -9 and 9. It has inflection points. So similar to the last example, they are telling you where the graph changes concavity at -6, -2, 2, and 7.5. Determine what could be said about the values. So let's just get an idea of what we could investigate. All right, so first of all, f of negative 1. So this is the graph of f, so we could just find the output. So at negative 1, the output is 5. Okay, 5 is a pretty big positive number. So f of negative 1 would be positive 5. F prime of negative 1. That means what is the slope right here when x is negative 1? That to me looks like 0. There's a horizontal tangent line there. So f of negative 1 is 5. F prime of negative 1 is 0. What about f double prime? Well, f double prime is located on a negative concavity. It's concave down, which means the value is going to be a negative number. So I have positive 5, 0, and a negative number. We are asked to put those in order. So when we go to do this, the negative number is the smallest, followed then by 0, which is f prime. So now I'm going to move over here, followed by the biggest number, which is going to be positive 5. So I would select my last choice, where this is the largest, positive 5, 0 is in the middle, and some negative number for negative concavity is going to be the smallest, and submit my answer. Okay? Here is Delta Math's explanation of what I just said out loud. This was the correct answer that I'm circling now. So for the fourth and fifth examples, we're going to really have to analyze and think about and move between the graphs of f and f prime. We're also going to have to answer the questions related to each graph and focus on the questions being asked in each part. So the background information is that this is a twice differentiable function. It means that you can take the derivative of f prime and also f double prime. They tell you the inflection points are at negative 5, negative 1, and 2, indicated by the small circles. Again, inflection points are where the graph changes from concave up to down or from concave down to up. Now we're going to make and draw some inferences related to the graph. Please remember, in this case, I was given f prime. So this is the graph of x versus the slope. Okay? So from this figure above, the graph of f prime, we're going to focus between negative 5, which is here, and 3. Negative 5 and 3. So slope, if I click on the drop down, right, we know that the slope of this is negative. Not the slope of this graph, but the actual m values are negative. They're below the x-axis. We also know that the slope is increasing. It's going uphill. Right? Because it's increasing, we can say that it is concave down. Okay? Notice the curvature of this is concave down. Now, based on these observations, on the graph of f, so not this picture per se, but on the graph of f, we would say that it is decreasing and concave up. Well, how do you know that? Well, we know that because if the slope is negative, doesn't that mean that it goes downhill? Slope is negative. The graph is going downhill on f. Not this picture, but if we went back to the graph of f. And it would be concave up because the slope is increasing. So notice here, we said that this slope is negative and it's increasing, which means if we go back to the graph of f, negative slope means that the graph itself is decreasing, and it would be concave up because the graph is increasing in its slope. On the interval -5 to -3, the graph of f double prime would be positive because f prime is increasing. Okay, so what we're saying here is the concavity would be positive because f prime is increasing. So again, f prime increasing is concave up. F prime decreasing is concave down. We can submit our answer and see the delta math explanation. Example, we're now going to talk about analyzing what happens at a specific point on both the graph of f, f prime, and f double prime. In our example, we're given a twice differentiable function. Again, f prime exists, f double prime exists. All right, it's got points of inflection at -6, -3, 1, and 4, but those are points on the graph of f prime now. Okay, so they are graphs on f prime, not the graph of f. So let's take this in pieces and answer the questions related to the given information. Based on the graph of f prime, when x equals -1, analyze the graph of f prime. So we know a couple things. On the drop-down menu, we know that f prime, the slope, when x is -1, is negative. Okay, so right here is where we're talking about, right where I'm pointing with the little cursor right now. And also, there is a relative minimum that exists. I'm sorry, not minimum, maximum. Because it's a high point on the graph of f prime. Okay, so we can use words like relative min and relative max when analyzing the graph of f prime. That doesn't mean that they're relative min or max on the graph of f, but they are for f prime. We can also infer, going back to the graph of f, when x equals -1, there is no horizontal tangent line there. And how do we know that? Because slope is going from negative, increasing, to negative, decreasing again. You can tell that here. Negative, it's below the x-axis, increasing, but then it's still negative below the x-axis, but it's decreasing. Slope has to change from positive to negative or negative to positive on the graph of f in order for there to be a relative min or relative max. Therefore, there is no horizontal tangent line there. We also know that there is an inflection point from concave up to concave down here because I went from increasing slope to decreasing slope. Increasing to decreasing slope is going to be an inflection point. Furthermore, we can state that f double prime is 0 going from positive to negative because there is a relative maximum when x equals -1. Okay? F double prime is 0. Remember, concavity is whether it opens up positive or opens down negative. At an inflection point, concavity is the switch from one to the other. Therefore, f double prime, the measure of concavity, cannot be positive or negative. It must be 0.